we can start our webinar. So welcome everyone to our last webinar series of iClimaBuild. And today we are going to listen to the presentation on innovative material solutions and testing for building envelopes from our expertise in iClimaBuild partners. And so today we are honored to have the invited speakers. First, Andreia will give a talk about overview of the iClimaBuild project, and then Asmaa will present about facade innovation, focus on smart ventilated heat harvesting window with Air-PCM Heat Exchanger. And after that, Vaia will present on the topic of improving indoor environmental quality, IEQ, and human comfort using 3D printed components. Followed by Matthias, he will present testing of new materials in Living Laboratories, which is a bigger scale. And the last topic is challenges related to building envelopes, presented by Eva. So during this webinar, I would like to encourage all the speakers that you can ask the question in the chat, or you can ask during the Q&A session at the end of each presentation. And so I think, and this webinar is recorded. And now I think we can start with Andreia. So please welcome her.
Good morning, everyone. My name is Andreia Araújo. I'm a senior research in composite materials in an institute in the north of Portugal, which is called Inegi. I will start sharing my screen, and the idea of this presentation, as the title says, is to give you an overview of the iClimaBuild project, from which the developments that will be showed today are come from. So this is just the outline of this presentation, and jumping right in, the iClimaBuild stands for Functional and Advanced Insulation and Energy Harvest Storage Materials across climate adaptive building envelopes. This project was founded by the European Commission in the topic Open Innovation Test Beds for Materials and for building envelopes. It's coordinated by Professor Kostas Karatidis from National Technical University of Athens, and joins together 27 partners across 14 European countries, from which 17 are RTOs and 11 are SMEs. So as you can see, this project has a lot of partners involved. The main idea of this project is to combine the development of materials in different pilot lines. We have also a core group of partners devoted to advanced characterization, another group of partners that deals with multi-scale simulations and visual performance analysis. Another part of the partners look into standards, testing protocols and regulations specifically for newly developed materials that are not covered by the common standards. And then we also have a huge core related to technology validation in living laboratories and also sustainability. The main goal is to create an ecosystem where different entities, and being like SMEs or large entities, high-tech developers, people from the building sector, and so on, to have access to different tools in order to test, validate, and upscale their new technological solutions that otherwise would be more difficult by themselves. So looking into more detail into the pilot lines, we have had 9 different pilot lines that were upgraded and optimized during the project duration, and I will give you a brief overview of them. Pilot line 1 is dedicated to the production of phase change materials, and this work is done by Rubitherm. Pilot line 2 develops flexible thermoelectric generators that can use different temperature differences to store energy that can power sensors. And this is done by our partner Technology. Pilot line 3 is dedicated to customizable 3D printed components for indoor comfort, and we'll be hearing more about this during this webinar. The partner that develops these components is Biogy3D. Pilot line 4 combines 3 partners, University of Dresden, RISE Institute, and University from Leipzig, HTWK, where basically they combine their technologies into composite sandwiches made of textile reinforced concrete and cellular lightweight concrete insulations. Our pilot line 5 is dedicated to the production of aerogels, which are lightweight super insulation materials. This is done by the University of Hamburg, TUHH. Pilot line 6, it's one of our, let's say, more sustainable or ecological pilot lines, and they produce insulation components utilizing waste materials. Here we have 2 partners, Tetma for the production of lightweight concretes, and Phoenix for the production of insulation mineral foams. Moving to pilot line 7, from my side, from Inegi, we produce multifunctional composite sandwiches using laminate fiber skins and insulation cores, and also we try to incorporate technologies from the other pilot lines into one final composite sandwich. Pilot line 8 from Fraunhofer is dedicated to solar active envelope materials and structures, and basically they apply the morpho coating to PV modules to give a more pleasing aesthetic. And finally, pilot line 9 deals with omniphobic coatings. This is done by Sidetech, and they are able to provide new functionalities to the outer layers of materials. For instance, to improve permeability, cleaning of the surfaces, and so on. These pilot lines were combined for the development of 7 different test cases that were developed, optimized, and then validated in Living Laboratories. Today, we will have 2 partners giving more information about 2 of these test cases. And as I mentioned, the test cases were validated in 5 different living labs across Europe, and each living lab corresponds to a different climatic zone. So we have for zone 1 and 2, the Anposta Living Laboratory from Eurecat. From zone 3, we have the Cube Living Lab from TU Dresden. For zone 4, we have 2 living labs, the YEC from Polito and the Living Lab at Manresa, also from Eurecat. And finally, for zone 5, we have the Z Living Lab from NTNU. Moving to the test cases. Test case 1 is the smart ventilated heat harvesting window. And as I mentioned, we'll be hearing more about this, so I'll just continue. Test case 2 is building integrated photovoltaic facades for energy production with an aesthetic pleasing form. So basically here we have the PV panels with a nice coloring, to, as the name said, to be more have a better design, a better aesthetic. The test case 3, it's a wall element that integrates a tag-powered humidity sensor. Test case 4 combines the materials from pilot line 4 and are considered thermally efficient and lightweight composite sandwiches. Test case 5 combines the materials using waste that can be produced in the form of bricks or blocks as new wall elements also. Test case 6 are multifunctional composite sandwiches made with different materials from different pilot lines. And also the idea is to improve the thermal efficiency of the walls. And last but not least, we have test case 7, which are the 3D printed customizable components for indoor quality. And once again, we have different variations that will be explained in more detail in one of the presentations today. To put this ecosystem functioning, we basically created different building blocks that correspond to different services that we can offer to customers, being the building block 1, materials by design, so everything related to materials development. Building block 2, testing, so we have gathered all the different characterization testing that are needed for this type of materials. The building block 3 deals with virtual performance testing and more with simulations and so on. Building block 4 aims to study the sustainability and safety assessment standards and regulations. Building block 5 deals with the upscaling of new technologies. And finally, building block 6 dwells more in terms of financing, investment, and innovation. All these services will be put together for customers through the single entry point and through a joint venture company that is being settled, and it will start working as soon as the project finishes. If you want to know more about the iCleanMyBuild project, please find us in the following links, or you can send us email or even myself for more questions. So if you want to ask me something now related to the project, please go ahead. If not, you can do that afterwards by email or checking all the information on the social media.
Yes, if we don't, do we have any question about iClimaBuild? And if not, yeah, then we move to the next presentation, Asmaa Ali. Thank you very much, Andreia. And yeah, again, you can try to ask through the chat. Yes. So welcome, Asmaa.
Thanks, Ned. Good morning, and thanks for having me. I am Asmaa Ali, an R&D engineer at Rubitherm Technologies, is located in Berlin, with around 5 years of experience in phase exchanger materials and its applications in a wide range of applications to be used. So welcome again to the webinar, and I am going to present an innovative test case of a facade component. This test case is about smart ventilated heat harvesting window with the integration of phase exchanger materials as heat exchanger. So this test case is given the name TC1 in iClimaBuild project, and I'm excited to share the development journey of this test case, starting with its aim, followed by the components integration and design, as well as testing and demonstration activities to measure and validate the performance. The aim of this test case is to supply the indoor with continuous ventilation of fresh air, as well as having thermal comfort of indoor. So windows are responsible for great thermal losses due to its poor thermal insulation. And during the ventilation, the conventional ventilation, by opening the window, a considerable energy losses happens. So this test case is aimed to overcome these limitations and provide the indoor with three main features or characteristics. As you see here, the first is the ventilation. We aim to supply the fresh air continuously, and this achieved by window and glazing structure, and I will explain it in more details in the coming slides. The second feature, we will have heat harvesting and storage to preheat or cool the air for thermal comfort, and this will be achieved by near-infrared absorbing layer and PCM storage component. And third, we will have want to achieve a good indoor quality by using 3D printed components for fan noise reduction and indoor carbon dioxide purifications. So the test case 1 consists of 4 components. The first component is the ventilated window and the glazing structure, which is consisting of exterior mechanically ventilated cavity and interior argon-filled chamber. And in the ventilated cavity, there is a near-infrared absorbing layer as well as low emissivity coating layer. And the second component is the PCM heat exchanger, which is based on a compact storage module made of aluminum casing, as you see here in this picture, with the dimensions of 450 by 300 by 15 millimeter dimensions, and it's filled with it can be filled with many different PCMs. For a standard filling of a PCM of SP21, which is a salt hydrate based PCM with a melting point of 21, it can be filled with 2 kilograms. The third component is 3D printed components. We have 2 elements, sound absorbing frames for the fan noise reduction and carbon dioxide capturing membranes for the indoor purification. And lastly is the amphibic coating that will be applied to the external glass for thermal cleaning properties. So to host the previously mentioned components, 2 casings or boxes were integrated to the ventilated window. So the upper box is will host the PCM components and the acoustic one, and it will have also additional ventilation that supports the lower mechanical ventilation and will help to operate the window in different operation modes. And we will have the lower box that can host the carbon dioxide filters and with additional components such as the ventilator and its noise reduction membranes. So 3 operation modes were defined for this test case 1. The first one is the supply air mode. It's an outdoor to indoor ventilation mode. So an external air will enter the ventilation cavity from the bottom, and it will be preheated by means of the near-infrared absorbing layer in this glass layer, and it will be preheated, and then it can enter the PCM heat exchanger for more control of the temperature before it goes into the indoor. So this mode can be used during mid-season or winter or part of the winter when there is enough solar heat to solar energy to use and to preheat the air. And in this mode, as you see, the PCM heat exchanger and the ventilated cavity are coupled together to provide the indoor with the thermal comfort. The second mode is outdoor air curtain mode. It's outdoor to outdoor ventilation of the cavity. And this is aimed to prevent overheating during summer. And in this mode, you see the PCM heat exchanger can be decoupled and work alone to provide the indoor with pre-cooled air. And last operation mode we defined is the thermal buffer mode. It's a baseline mode, and it can work to reduce the heat losses. And the same also here, the PCM heat exchanger can be decoupled from the glazing configuration, and it can be operating in very cold days in winter. So to test this test case extensively, we came up with testing in two different levels. The first level is the component level test, and in this way, we have defined 4 tests to be done. The first test is to select the fans that will be integrated for the heat exchanger. And as I said, the ventilators here can support the lower ventilation, as well as can operate the test case in the other 2 operation modes when the PCM heat exchanger will be decoupled from the glazing configuration. And we also wanted to test the full PCM air heat exchanger performance, and we have 2 characterizations to be done here. So the thermal characterization of the heat exchanger, as well as the pressure drop across the all components and the acoustic component as well. We also wanted to test the carbon dioxide filters, and finally we wanted to test the fan's acoustic characteristics. In a full-scale testing, we have defined 3 more tests. One will be in a full-scale lab testing in a climate simulator. It's still lab-controlled testing, and that's why we came up with testing in outdoor test facility that's close to the real conditions. And in both tests, we can measure the U value and G value, and also we have defined other thermal efficiencies. And last test we will have is acoustic performance, and this will be done at HTWK in Leipzig. And in this test, we will test the facade sound insulation and the insulation against noise generation by fans when we use the acoustic absorber and without. So the first test, when we came to select the best fan, so we choose one of the 3 fans. So starting with a low performance axial fan, but less noisy, and high performing centrifugal fan, but very noisy, and a middle one of blower fan with middle performance in both acoustic and power performance. So after many tests, we concluded that 2 axial fans are comparable to the one of centrifugal fan with high performance, and we will use 2 axial fans in series, and this will also help in decreasing the dimensions of the upper box. Coming to the second test of PCM air heat exchanger, we tested both thermal and pressure drops. So the thermal, as you see here, this is the unit, the first unit that was fabricated, and here is how it's seen from inside. You see the fans, 2 fans in series, and the PCM the PCM plates, and we for every unit we have 5 plates parallel to each other, and finally we will have the acoustic absorber, as you see here. So the thermal performance was tested in climate chamber at ERICOT, and here you see the sensors distribution, and here this is the setup of acoustic and of pressure drop across to be tested for the heat exchanger and the acoustic absorber. So from this test, you can see first we tested the performance with different delta T's, and here the PCM used has a melting point of 25 degrees Celsius. So we tested plus 10 degrees higher and minus 10 degrees differences, and we changed this difference from 10 degrees to 7.5 to 5 to 2.5 degrees Celsius to see how the PCM can control these differences when it comes to the real conditions. So here these two sensors, you see from the beginning and the end of the plates, you see a big difference. So that the air comes here in a high temperature close to 35, for example, and ended here to temperatures for a long time around the melting point of the PCM, and it has shift in both temperatures and time. So we have, as much as the temperature difference increases, the PCM can regulate more the indoor, and it can provide with more consistent temperatures. So these are temperatures of lower and middle sensors of the plates as an examples. Coming to the pressure drops, two tests were performed here: the acoustic drop across the acoustic absorber alone, and then the complete unit as it's shown here. So in this setup, we have tested different airflows, and it was found that the acoustic absorber pressure drop was not so big, and it's smaller than the pressure drop across the whole component. And here's acoustic absorber across the pressure drop across the acoustic absorber was exponential behavior. However, for the complete unit was like linear performance. And we used the fan of the normal unit, and we verified it, and it was in line with these two tests. And however, the pressure drop is high for the complete component, but it still delivers a very good airflow velocity. Coming to the carbon dioxide filter testing, in this test we used only 5 filters, but in the final test case we will have 25 filters. So as it's shown here, we have performed many pulses. The pulse duration is 20 seconds, and these 5 filters is tested in multi-purpose air chamber where carbon dioxide dosing is introduced in one side, and the evolution of this concentration is tested in the other and recorded in the other side. So from this figure, you see regular trend that happened from the second pulse with average of 67% attenuation, and this is only for 5 filters. Coming to the full-scale testing, tests were done in outdoor test facility at Polito, and here we have defined different KPIs for as a standard testing in such components. U value and G value are normally tested, and we also defined outlet temperature between 17 to 25 degrees that should enter the indoor, and we have defined different efficiencies, and such as thermal buffer efficiency in thermal buffer mode, preheating efficiency in air supply mode, and dynamic insulation efficiency in outdoor air curtain mode, and this efficiency should be close to 1. And for this heat test case, we will have thermal storage capacity of around 1 kilowatt hour per meter of the facade, and this defined by the number of the PCM plates and PCM filling in the heat exchangers. So the ventilation flow rate was also defined between 50 to 100 cubic meter per hour, and light transmittance between 50 to 55%. And finally, we will have acoustic KPIs. So to verify these KPIs, first, ventilation flow rate was tested in outdoor test facility. And as you see here, a correlation between the fan percentage and the flow rate, as well as the maximum design flow area for the space given here. So using 10%, only 10% of the fan can ventilate until 9 cubic meter square meter of the space, interior space, and using 100% of the fan can ventilate until 22 square meter of space, interior space. So so this ventilation flow rate can be achieved. So as I said, 9 to 22 square meters of interior space can be ventilated with only one PCM heat exchanger. And however, for outdoor air curtain mode, the number was the half, and this could be given to the pressure drops developed across the pipes. This, of course, can be improved, however, is still sufficient and in the predefined KPIs. And the light transmittance, it was found that it falls into the range we also defined by 50%. The U value, it was found between 1.2 to 1.8. However, we defined 0.9, but using the simulations, this was given that not realistic, because the simulation of such configuration was in the range of 1.15. So this also depends on the operation mode, and the outlet temperatures that was defined between 17 to 25 degrees Celsius was able to be achieved between 40 to 60% of the time in supply air mode, and 50 to 100% of the time in outdoor air curtain mode. Solar factor J value here, it was defined by 30%. However, it was found to be 25% in supply air mode and much lower, 20% in outdoor air curtain mode, and this is given to the ventilation, which proved to reduce the G value. Coming to the efficiencies that were defined, so it was found that preheating efficiency in supply air mode at 1, to be close to 1, that was achieved in 50% of the time, and the dynamic insulation efficiency in outdoor air curtain mode was between 0.7 to 1 on average. So here, as you see, this test case was demonstrated in living labs. So we have 3 living labs assigned for this test case. We installed 2 modules in ZIP Living Lab in Norway, and 1 in TB Living Lab at Boleto, and this office building. And finally, we have 1 module installed at Ambosta Living Lab. Coming to the test performed at the ZIP Living Lab, first smoke visualization for the airflow and speed was shown here. As you see, of course, the more heat flow is giving to the percentage of the fan used, and the correlation between the airflows with and without acoustic absorber was also measured. With acoustic absorber, we have half of the flow rate, airflow rate given with the acoustic absorber, and yeah, still despite this reduction, but still can be achieved, and as a ventilation we already defined. So here also a thermal test was done in March, as you see. So the outdoor temperature was between 5 to 10 average. However, the indoor temperature could be achieved close to the comfort level of 20 degrees, and these two lines, the blue and the orange, are given to the two modules, left and right, and you see even when during the peak hours here, the heat absorption was too high with in the ventilated cavity. However, after entering the air through the PCM heat exchanger, the temperature was dynamically controlled by means of the PCMs, and this can be achieved by absorbing the excess heat by the PCM and releasing it during the night when the heat is required. Yeah. There is also a feedback from the users to be involved in the Living Lab to share their experience and interaction with this test case. And for example, this test, some of the data recorded from the TB Living Lab at Boleto, and the test is still running and should last around 7 months. However, the recorded data is good. For example, here regarding the thermal comfort, we have here the big contribution to the comfort, that it's comfortable, and it's the same for the visual comfort. However, it's more here for slightly annoying in terms of the noise and also the smell of the test case one. And yes, the test is still running, as I say, but it's the data is subjective, of course. It depends on the user, but the initial results is good in terms of the interaction of user with the test case. So another thermal test was done at TB Living Lab. So here you see first the configuration of the sensors and the curves you will see here. So the blue represents the inlet temperature from the lower part, and the orange represents to the outlet of the ventilated cavity, and the gray here represented the outlet of the PCM heat exchanger. And this was done in supply air mode in winter, and you see the PCM was able to bring the temperature even closer to the comfort zone, which is close to 20 here at the set point. So here a representation of how much is the PCM can contribute to this. So, for example, the PCM was able to reduce the times when the temperature is less than 20 and increase the time and percentage of time when the temperature was close between 20 to 26, and also the reduced the time percentage when the PCM was, the temperature was more than 26 degrees. So coming from the phase change material background, I would leave this message that PCM helped to bring the temperature close to the thermal comfort, and it's able to dynamically regulate the temperature more by absorbing the excess heat and preventing overheating and releasing that heat when the temperature and heat is required. So thank you so much, and yeah, for future communication or questions, please feel free to contact with me.
Thank you very much, Asmaa. We have time for a short question. There is some ask. So if not, I would continue to the third presentation. So Vaia. Okay. Please welcome Vaia.
Hello. Thank you everyone for joining us today. I will briefly introduce myself. My name is Vaia. I'm an interior architect and product designer, and specialized in computational design. And as such, now we will change subject and dive into topics related to interiors. Okay, can you see my screen?
No, not now.
Not yet.
Not yet?
Yeah, now it's coming. Yes.
Okay. Okay.
Yeah, it's coming.
Okay, so and more specifically, we will dive into the domain of indoor environmental quality and human comfort. According to the European Commission, people spend about 9% of their time in indoor spaces, such as residential and office environments. The indoor environmental quality of a space, which accounts for the visual, acoustic, thermal comfort, and indoor air quality, has effects on the occupant's health, well-being, and overall comfort. And poor indoor environmental quality may actually have adverse effects on work productivity or even cause the onset of diseases. So within the scope of a climate build, I'm sorry, I think there is a delay when changing slides. Within the scope of a climate build, we have targeted these challenges by capitalizing on 3D printing technology to develop highly customizable, performance-driven applications that can act complementary to envelope materials as indoor functional surface finishes that also prioritize human comfort and appealing through aesthetics. So during the course of the project, we have developed a series of components related to 2 test cases for these products. Most aspects of indoor environmental quality have been taken into consideration, capitalizing on various additive manufacturing technologies and materials, but also the customizability aspect, mainly enabled through computational design and parameterization. For example, in the case of test case 1, casings with customizable number of functional panels have been developed, integrating both sound absorptive and CO2 absorptive properties. This has been targeted through a series of flat panels with an intricate pattern and foaming properties in order to force capturing of the sounds while not stopping the airflow needed. Respectively, a series of panels with electrospan membranes, membrane filters made of custom formulation of metal organic frameworks have been developed. Now, moving on to the passive 3D printed components, 3 applications have been developed. Test case 7.1, which refers to panels with integrated light diffusers. Test case 7.2, which refers to hybrid acoustic panels with sound absorptive and diffusing properties. And test case 7.3/7.4, which refers to ceramic applications with humidity absorptive properties that help passively regulate the temperature of an indoor space and therefore act as passive coolers, but can also absorb CO2 to improve indoor air quality. As already mentioned, customization has been an aspect of utmost importance for all applications. And this aspect refers to customization in terms of design and materials and assemblies on a spatial level. The tested formations are therefore only indicative. And as the main scope was all the systems to be easily expandable to satisfy the performance needs of any interior space. Taking that into consideration for the light diffusing panels, a series of design and benchmark values set as KPIs have fed a preliminary computational design workflow to determine expectations in terms of design, assemblies, and material formulations. For the design of the diffusers, various patterns have been tested. The objective here was to develop a parametric design methodology for variations based on a phyllotaxis pattern. Phyllotaxis in nature is the best packing method for a high number of single units. This essentially means packing of a high number of detailing features around the z-axis without overlapping. As a first step, extruded patterns with non-rotated or rotated cavities of a single or variable diameter have been developed, as you can see on the left of the screen. And as a second step, flat and convex surfaces, as well as fine features such as beads and cavities and thicknesses, have been parameterized. Now, as an intermediate step, custom photocurable resin materials were formulated with light diffusing agents and undergone printability assessments to determine fine feature tolerances. The various designs were then printed and tested according to the KPI sets in order to select the optimal design and material combination. For the demonstration and for validation purposes, the single light diffusers were then integrated in a saddle-like perforated scaffold closed with a lid containing an integrated dimmable lighting system with LED strips, with all of them forming a single lighting unit. And finally, a testing campaign has been launched starting on a material level with a 3D photogoniometer to measure the BSDF properties of the components, the light output ratio on a lab scale level, and KPIs such as the workplace luminance and the unified glare rating on a spatial level as required by the respective standards. Now moving on to the acoustic panels. What we have tried to accomplish here was to integrate both sound absorptive and diffusing properties. And this is essential for an indoor space in order to balance acoustic comfort, speech intelligibility, and spaciousness, while avoiding reflectance or spatial numbness caused out of extreme sound absorption, for example. This has been targeted through the implementation of a series of design typologies aiming for different frequencies, within the human spectrum, as well through customizable material properties. Due to the thermoplastic material with foaming agents that activate at a certain temperature. For the diffusing properties, a parametric design methodology has been developed for variations based on true step surface irregularities. While for the foam core, the macro porosity has been customized through a geroid pattern. The dual functionality, of course, would not be feasible if not for the allocation of the variant material properties, as you can see on the right of the screen. Capitalizing on the local and thermally assisted activation of the foamic agents integrated in the lightweight thermoplastic material. And this approach led us to the development of 10 panels used for the test case. To conclude, the proposed design methodology paves the way to a customizable large-scale cumulative acoustic performance by varying the parametric step thickness. An interlaboratory study with Polito helped us address the challenges on a material level analysis in an impedance tube with respect to the representativeness of the test samples and their relevance to the original panels. And further testing involves analysis of absorptive and diffusing properties in a small-scale reverberation chamber and in-field measurements in living laboratories according to the respective standards. Now moving on with our last application, ceramic components with humidity and CO2 absorptive properties have been developed, and the functionality of these components is based on the employment of local aluminosilicate materials, powdered materials, which are then make part of the pastes used, and they have increased surface area. In terms of design, parametric design methodology for variations based on a space filling curve has been developed, representing differential growth commonly seen in natural systems, whereas as an assembly strategy, a puzzle logic has been followed that allows for self-interlocking to minimize complexity. For the material developments, material stability and dimensional accuracy have been extensively tested both on a liquid state during the liquid deposition modeling procedure and during the solidified state after a sintering procedure. As an optimized design, after several observations during the tests we have conducted, we have concluded to this design consisting of an elastic photocurable resin-based scaffold and 3 ceramic absorptive components. And as far as it concerns the testing of the test case, the same logic has been followed for testing on a material level. So the CO2 absorptive properties of the material, of the crushed material, has been tested using a thermogravimetric analysis and fixed bed reactor in collaboration with SINTEF. Whereas another aspect of utmost importance for our case has also been tested, which is the antimicrobial properties of these components, which are basically exposed to humidity. So we had to confirm that no bacteria would grow on these components, which has been confirmed with the respective test undergone by our partner NTUA. Furthermore, on lab scale, the moisture buffering value, their ability, the capacity to absorb humidity, and the CO2 absorption capacity of the components has been tested. Whereas the application is currently under monitoring in living labs in order to define the respective KPIs. To conclude, 3 applications, 3 3D printed applications for indoor environmental quality improvements and human comfort have been presented. Referring to visual comfort with light diffusing panels, referring to acoustic panels for sound absorption and diffusion to ensure acoustics, good acoustics in space and speech intelligibility. in an office environment, and an application of passive coolers, basically air conditions without the need of energy, and CO2 absorbers for indoor air quality improvements. For any information you may need, I will be happy to get in contact if you want to get in contact with me. So yeah, that's all on my side.
Okay, thank you very much, Vaia. Any question? If we don't have any question, then we can move on to our fourth presentation. Matthias. Matthias, let me check.
So very good.
Oh yeah.
Sorry, I was I don't know why, but I was blocked. So my microphone doesn't work, and also my camera. Sorry for that. I don't know why, but now I think everything is fixed and we could start.
Yes.
So first of all, I would like to introduce myself. My name is Matthias Tietze. I'm from Dresden, from the Technical University in Dresden. We are responsible for one of the living labs, one of the 5 living labs. They was also presented very short before in the first presentation from Andreia. And we are, we have a good, or I have a short presentation for you to show you the Living Lab Cube and what we did in them, or what we do in them. Oh, that's better. So I hope you see my presentation.
Yes.
Yes, very good. Okay, I will give you a short overview about the Living Lab Cube. It's located in Dresden, and also the test cases we implemented in. This is a short agenda. I tell it before so we can step over this slide. This is the Living Lab Cube in Dresden. It's on the TU Dresden campus. It's an experimental building in carbon reinforced concrete. Every components are built in carbon reinforced concrete. If they are not windows or something else, technical stuff and so on. So they have 2 very interesting parts. One of them are the twist elements. You see it. These are very light concrete shells. They are curved and they are a wall and a roof and all in between. And so we could show how we could or what we could do with carbon reinforced concrete now. And also we built a box. This is this black thing where the white square is around. This is a prefabricated part in carbon reinforced concrete. And in this box, there are 3 rooms implemented, integrated, where we could implement our test cases. This is, so we say, our test area in the cube, and I show you a little bit more detailed how it is structured and so on. We have 3 rooms. I think they are nearly the same, have the same size. We use it differently, but it's the same size, and it's classically used as a testing room and also as an office room, and also for seminars. And so we have every time people in them. Our test elements are implemented. You see it in the pink square on the right side and on the downside. This is implemented in a window construction, a post beam construction, typical for business buildings or high-rise buildings with a glass facade, and we use them because it's very easy to implement new elements and to bring it out, bring it in. And so we use 2 parts of this window area for our testing elements. You see it a little bit closer where we implement our elements. The elements are 60 centimeters wide and high and up to 30 centimeters thick. So this is the range where we could work in. This is our typical measuring technology or the measuring methods we use. We measure temperatures on the surfaces, inside and outside, of course, with all of our elements or elements are von Almeno. We measure also the temperature and humidity. You see it on the right side and on the cross section with these 2 points, red and blue. And also we use a head flux plate to measure the head flux, the temperature. And also we have a data logger. They log the data every 3 seconds, and then we, after all 5 seconds, we do an average of this data, and we bring it in our data management system for the partners. I have also a little sketch here how it works from the measuring system. We collect the data from them every 5 minutes, this average data, and we put it in a Linux client. And then we use a typical cloud system. It's named Data Share TU Dresden, and we push it into the cloud, and everybody who has access on these web browser, he could get the data from us and could analyze it. So what is actually implemented in the cube? These are 4 test cases. We started last year in end of spring with test case 3 and test case 6 from Inegi and from RISE. After this followed the test case 4 from the colleagues from Leipzig, HTWK, and in this year we implemented also the test case 5 from the colleagues from Asmaa. Though these are all these elements we are implemented, you see before only three slots for the elements where we created 1 more slot, but in a later slide I will show how we do this or how we did this. So for you and for the location, how the test cases are installed. Now here very short in test case 3 is implemented in the middle room, in the room 2. It's not a reason why it's in the middle, because it was the first the first slot we have opened, and so we installed the test case 3 at the first element in the test in the room 2. On the right side, you see the installation of the measurement system, typically. So the next test case is the test case 6. We implemented in room 3. In the same way, we implemented also test case 3 because every element has nearly the same dimensions, and so it's for us very easy to put it into the test case slots and implement all the measurement systems. This is test case 4, nearly the same element. This is located in room 1. And test case 5, this is the last test case we could install, is also implemented in room 3. We used a bigger area for that to implement this test case. So we used another space. They were used before for other measurement, but now we are able to measure all these test cases until the end of the project. So how are the test cases are developed, or what are included in these elements? I stated before, we had every time nearly the same structure with nearly the same layers inside and outside. Every time with a concrete or mortar shell. On test case 6, you see it's inside and outside a very thin mortar shell with there are implemented also an aerogel between or after the mortar shell and before the express foam comes. There are very thin basalt laminate implemented. Then in the middle, a 20 centimeter thick express foam for the insulation, of course, and the inner shell has a special also implemented 45 CSM element for the phase change thing, and also it's a very thin layer of mortar over them. It's a very fragile element, but I think, or I hope, the measurements would be very good test results. This is test case 3. This is all nearly the same structure inside and outside, also a concrete shell. It's connected with thin rebars in glass fiber. They use 4 elements of them to connect the inner and outer shell. In the middle is a new insulation material, and also you see it. It's only a square in the middle of the sketch on the right side. It's also an element for measuring, for example, humidity. It's a sensor. They used the so-called Seebeck effect to get the energy from the difference from the inside and outside temperatures, and with this energy they can send the data out of the element without any other energy you have to put in. And maybe this could be a very good way for buildings to check the data on that. So test case 4, this is the test case from HGWK. Inside, outside also a concrete shell. You see it also connected with the thin shock rebar elements, or they use also 4 elements. They don't have an extra sensor inside, but they use an aerogel insulation. I think it was a granulate, and they pressed it and bring it together. And so I think it's a very lightweight element and a very I think high U value with this material, or they reach a very high U value. And also the element from Asmaa, this is, you see it before in the other presentations, is an element with also inside, outside a concrete shell, but it's a lightweight concrete. And in the middle, it's a mineral foam, and everything is also connected with 4 of these connectors in glass fibers. So we implement this element also. And now I have some pictures for you how we implement it. It's I think it's very easy in the cube to implement it, because the elements are in a height of up to 1.80 meters to 2 meters. You don't need any technical support, so you could do it with 2 persons and put it in. On the right side, you see the installation of the measurements. This is TC3. It's nearly the same, but I think we change the head flux plate on the right side, because in the middle is the sensor. So this is, I think, a little bit older picture, but you see it's on the same way. We put it in, and then we could close again the post beam system, and everything is fixed. And here the TC5, for this we have to replace a bigger element, and now we change it in 2 smaller elements. On the left side, we could put in the TC5 with all the measurements inside, outside, temperature measurement, and also head flux plate. And everything is now fixed, and we will measure it until the end of the project. This will be with a prolonged, I think, in 2025, maybe in June or in July. And here the implementation of test case 4. For this, a little bit detailed informations. Here we installed the humidity and also the temperature sensor inside of the element. We made a little hole and in the foam, and put the sensor inside. You see it on the picture. And then we could bring in the element. Before we have to prepare it on the frame, and then we could install it. So after this, we install all the measurement elements, and everything was fixed. And then we do with our administrator the connection to the data collection system, and then everything was installed and could use by all the partners. So We have also some results. I said it before, we log the data every 3 seconds, and the average comes every 5 minutes into the data store for every partner. We do it with the head flux, for example, here, test case 3, test case 4, test case 6 in February this year. Also surface inside, and also surface temperature outside. This is over only 1 day. And element temperature, of course, and element relative humidity you could also check. In the end, maybe a little bit more about our work, also in the materials, especially in the wall elements and the different layers. In case of new material development, and also in case of the circular economy. We have the situation now that we have in actual buildings up to 25 different materials in wall elements. This is very much. And so maybe in the future, we should think about also in the development of new elements, building elements, how many materials we use in case of the recycling, and also the circular economy. So it's I think it should be much better to use less material. We try it with maximal 4 different materials in one wall to bring all the requirements into the wall and have all we could all applicate all the things we need in these elements to have a very I think a sustainable solution for the future, and this should be the idea for the development of next building systems and elements. So thank you so much for your attention, and I hope we get some questions, or you could get contact with us. This is my email address, and feel free, and thank you for your attention again.
Thank you, Matthias. Again, is there any question? Okay. I guess maybe after that, after this webinar, you will have some emails and question.
I think
so. Yeah, but thanks a lot for the interesting part of Living Labs. So now we move to our last presentation. So Eva from Rice. Yes.
Yes, thank you. Okay, and I will, I suppose you see my screen.
Yes, now.
Yes, I'm working at Rice as researcher in the area of building physics. And my topic to this seminar is the challenges related to building envelopes. And since I am a building physics, it will be in the perspective of building physics. And when we develop new products, we have a purpose. And the main purpose, the goal is normally, I would say, maybe not in all cases, but very normally, it is to ensure a good indoor climate. And with our buildings, we do it to resist wind, rain, snow, heat, cold, noise. and there is more. But this is the most common. And then we can also have some other contribution with our thermal envelope. It could use low energy. It could also produce energy when we use solar panels on it. And as we heard in the first presentation today, we can also use windows to heat recover, to preheat air in the building. Windows also give the benefits that it let lights in. So there is a lot of function that we could have with the thermal envelope. And I will just mention some of the most important challenges when we develop new ones. So what do we have? My examples for today's. We have the prevention of wind and air. Wind is from the outside, but we also have to prevent air from the inside to get out in the construction. We have rain, of course. We don't want to have leakage in our buildings. Depending on where the building is, we also have to prevent snow. And of course, we have heat and cold, depending on if the building is located where it's hot or where it's cold. Another thing that is quite important is the noise. It could be traffic jam outside. It could be overhearing between different rooms in the building, and we need to prevent it. So if we miss the first challenges with wind, rain, snow, heat, cold, then that will affect thermal comfort, the energy use, and it might also cause moisture problem. If we fail with the noise, then we somehow will have some health issues, or someone doesn't want to use the building. Okay. So some discussion about the wind and air. This is a very common construction in Sweden, where I come from. It's an ordinary one, and very often there is no problem with the construction itself, the solid construction. You can see in this picture, there is a foil on the inside to prevent air coming from the inside to the outside. And there is a airtight board on the outer side to prevent wind to penetrate the construction. That's the normal way. And this works well. The construction doesn't need to look like this. It could have been a sandwich concrete element, but the element itself is normally really, really good. The problem is that we have all the connections. A building doesn't only exist of a wall. It is a wall connected to a roof. It's wall connected to a wall. It's wall connected to a roof, to a floor, and so on. And we have windows mounted in it, and we have doors, and so on. So there is a lot of different connectors. And those are the ones that normally cause problem. And when we have a problem, it could look like this. When we look at the construction with an IR camera. This is a window mounted in a wall, and it's not airtight. You can see the dark color and how the air almost is flowing inside the building. The same thing here. It's not a hole. It looks like it's a hole, but it's not. It's a connection to power where air can flow in. Both those figures or problems when we have airflow into the construction. This is airflow from the outside to the inside. In this case, it's cold air coming in. It will cause higher energy use, and it will also affect the thermal comfort. But we could have the reversed situation where we have warm air going from the inside to a colder outside. And in this picture, you can see there is warm air. It's not tight in the corner. So normally we have a little higher pressure on the inside, close to the ceiling. And we can see we have warm, moist air going out through the little opening in the construction. And when it meets a colder surface, it becomes condensation and moist problem. And it's what we can see in this lower left figure. So we also have to prevent the air leakage from the inside to the outside. If you have a warmer climate, this is not that big issue as it is when you have a cool climate. That was the wind and the air. And we also have the rain. Of course, we don't want to have rain leakage. And we test a lot at the laboratory at RISE. Normally we test windows, because if you have a rain leakage, when you have a window or a glass facade system, you can see it very quickly if you start leaking. So that's why we test a lot. And normally you think that it's obvious that a window or a glass construction should be rain tight, but it's not. It needs to be tested and verified. But it's not only the windows and the glass system, because we also have leakage in fully constructions. And that's much more difficult because we don't see it. If we have a leakage, the rain stays normally inside the constructions, so we never see it until it has caused a huge problem, and that could be a couple of years later. And I have an example where we have tested different solution of how to mount windows in a sandwich concrete element, just to show that there is also tricky with this kind of constructions. So it's 6 different mountings that is tested in our chamber at RISE. And this is made in an other research project, just to see how, because the concrete element itself is tight. It's when you connect it, you have a problem. So 6 different solutions, and we have different results. And this is probably quite small. All those staples with different colors shows when it starts to leak rain. So the yellow ones is already between 0 and 10 Pascal. And we can see we have it for 2 of the windows. There is a rain leakage already at that low wind pressure. And it's wind pressure in combination to rain, I have to say. So this is just to highlight that you have to be careful with this, because it's very easy that you have a leakage. Another thing, if you have snow, I would say rain normally fall down. It needs a wind pressure against a surface to be pressed upwards. It can also be, yes, rain can go upwards, but snow, it doesn't need much more wind pressure at all. It's very easily go upwards, as you can see in this figure. And it means that snow can get in on much more places, and that will result in pictures like those. As long as it's cold, no problem, but you know, this will melt and become water. And then we have the heat and the cold. And those are probably the most important when we talk about energy efficient building. This is what we normally have focus on. And the heat and cold transportation in a construction is prevented or made mainly by the thermal insulation, and we have also thermal bridges. We have a lot of different thermal insulation. It's a huge amount of different material that could be used as thermal insulation. And we also have thermal bridges. It's a bit tricky, and they are also caused mainly by the construction and how it's made, and also by which material is used. About the thermal insulation, normally it's very easy to select and change insulation in a construction. And when you should choose an insulation, I think it's good to not only see to the thermal values. Of course, the insulation ability is very important, but you can have much more benefits from the insulation as well. So also think about the air permeability. There is insulation material that isn't air permeable at all, who could prevent the air to get in. If that is important or not, it depends on the construction you have. And insulation material could also have hygroscopic properties. It means that it could absorb moisture from the construction, from indoor, from outdoor, if you want or not. You could have stability or strength. The insulation could help the construction to become stronger, higher strength and stability. And also the mechanability. It's how the carpenter, how easy it is for a carpenter to handle the material on site. And then, of course, you have a cost and also an effect on the environment. How sustainability the material are or is. Okay, so it's a lot of things to think about when choosing an insulation material. One funny thing with insulation material that I think is that this is the result from project made now, I think it's maybe 13 years ago. It's end of 1990, where a lot of institutes in Europe have measured the thermal conductivity of different materials. And all results are selected in this graph. And as you can see that all material follow the same behavior. And this diagram shows the thermal conductivity depending on the density. And all those dots with different colors and different shape forms are different materials. And we can see that they they have the same shape, and when they have lower density, the thermal conductivity is also lower. And it's quite independent on what kind of material it is. It's the density who is the most important. And the lowest limit here is around 0.028 or something, the bottom of this figure. And that's the limit from the air. That's the thermal conductivity of the air. So that's the lowest limit. But I think you also notice that you have some material which is not follow this curve. And those material, that's the material where we don't use air as to prevent the heat transport. This is polyurethane foam, different ones. If we had aerial in end of 19th, it would be even a little lower. And if we would have vacuum insulation panels, it would also have been even lower here. So that's the fact, the simple physics of insulation material. So if you know the density, you can almost know what value the material will have. Okay, I will continue a little about thermal bridges because I know they are tricky and quite important when you work with new kind of constructions. We don't want to have thermal bridges, but we can't avoid them because they are everywhere. Everywhere where we have less insulation or where we have a corner or a connection. And we divide them in linear one and point ones. And you can see here I have marked them in red, typical places where they are. All where you have connections. Windows, against floor, balcony. We also have point thermal bridges somewhere. So there are a lot of them. So we can't neglect them. And one thing that is a bit tricky with thermal bridges is that they are the values are relative. So the value of the thermal bridges is relative the construction without thermal bridges. So if you have a really good construction with a low U value or a high thermal resistivity, you will probably have a higher thermal bridge. And if that is difficult to understand, I have a short example, calculation example. If we have a wall with a pillar with inside there, the pillar works as a thermal bridge. And so we have the construction with the pillar and we have the construction without the pillar, without the thermal bridge. I put values on this construction. I say it's 20 centimeter insulation. The lambda value of the insulation is quite high, it's 0.04. And the pillar is made of wood. It has a lambda value of 0.14. So what I do when I would like to calculate the thermal bridge is that I calculate the heat loss through the construction when I have the pillar in it. And I got a value. In this case, 0.275. And then I calculate the same construction, but without the pillar. And I got another value, of course, lower, because here I have no thermal bridge. And then I calculate the thermal bridge. And the thermal bridge is the difference between the heat loss when I have the pillar and the reference value. And I got a value. In this case, 0.075. If I have the same construction with the pillar, but I change the lambda value of the insulation from 0.04 to 0.03. That means I have a better insulation. And if I calculate the heat loss when I have the pillar you can see the value become lower because the insulation is better. And I also calculate it without the pillar. And of course, this value also become lower compared to this one, the first one. And now when I calculate the thermal bridge, I do it exactly the same way. I have the heat loss when I have the pillar, and I have the reference value without the pillar. And then I got thermal bridge. That is higher than the first one, 0.083 instead. But still, the last one, the last construction is better because I use a better insulation. So that's one of the tricky things with the thermal bridges. It's very normal that you focus on the specific value and you want it to be as low as possible. And of course you want it to be as low as possible, but a high value can also mean that it's because the surrounding construction is really good. So you need to see to the whole construction. Okay, I continue. I had come to the end of my example about what I think is important to think about, the challenges when working with new envelope constructions. And I will also mention that this was just a selection from my side. And when I made this presentation, when I come to this last slide, I also realized that this is not all. We have more challenges. For example, I haven't mentioned much about the noise and how to prevent it, but it also come up to me that we have radon gas that we have to think about. And I'm quite sure that you also have more things. So have in mind that this was only an example about what I thought was the most important to have in mind. So I say thank you so much for listening, and I'm open for question if there is any.
Okay, thank you, Eva. Any question? So this is the last chance that we can ask the question in live. Okay, if there is no question, then I would like to thank all the speakers of today, Andreia, Asmaa, Vaia, Matthias, and Eva, for a nice presentation today. And so in any case, if you have question, please feel free to contact all the speakers, and also please follow us on iclimabuild.eu, Facebook, and also LinkedIn and X. Yes, I would like to close the webinar series of iClimaBuild. Thank you very much for all participants as well, and hope to see you next event. Yes. Bye, and have a nice day.
Thank you.
Bye-bye.